Okay, you can hear me, right? Now, just now we stop here. That is, if let's say the MLE involve the ordinary deductibility, or maybe maximum cover loss, or maybe the policy limit. So if involve the deductibility that we have learned already, the factor is the PDF of each individual observation divided by the survival and deductible. Okay, so if you have if you have a maximum cover loss, then you may take this survival at maximum cover loss divided by the survival at this D. Okay, so if you have just policy limits, okay, then you just take this survival. If you learn also, right, the only the policy limit that is survival at the policy limit and divided by the survival at D. Okay, so today we have learned, I think is only this maximum cover loss. I think the rest, I think we have learned before. Okay, for the deductible, yeah, for the deductible, we have learned that is before example 8. Okay, we have learned, and also policy limit, we have learned in example 7, before example 7. Okay, so now we just involve a new one, that is the maximum cover loss. So the maximum cover loss actually is the same as like policy limits, right? Take the survival, okay, and then okay, and so on, class. Now we go to the example 10 now, okay?
Example 10. A policy has a deductible of D, which is given by 3, and a maximum cover loss of U star, which is 14. A random sample of 6 insurance payments is given as follows after the deductible is applied. Suppose that the ground up loss distribution is exponential with parameter data. Find the maximum likelihood estimate of parameter data. So let x be the random variable such that x is exponentially distributed with this parameter data. So given this observation, that is after the deductible is applied, that means this is referred to the observation for yi. So we have to convert to xi, that is the ground up loss data, where the xi, which is equal to yi plus d. And next, we try to apply the factors to form the likelihood function. And hence, we will get the log likelihood. So by taking the optimization from calculus, then we can find the maximum likelihood estimate of this parameter data. That is to get this. Solution for example 10. Let x be the ground up loss random variable such that x is exponentially distributed with the parameter data, where the PDF and the survival function is given by this, subject to a deductible D, which is 3, and the maximum cover loss, which is 14. Let y be the random variable of payments after the deductible is applied. Then we will have the following chart for the observation yi and xi as well, where xi is equals to yi plus d. That is, this observation can be obtained when the yi observation plus the deductible. Now, since this 2x value, which is equals to the maximum cover loss, therefore, we will have this factor. and repeated twice. And for the first 4 x value, which is less than the maximum cover loss, then each of these observations will contribute a factor of the PDF divided by the survival at the deductible. And hence, we have the following result. So, after you simplify this product, you will get this result. And next, we try to find the log likelihood function. That is negative 42 over theta minus 4 log theta. And therefore, the first order respect to theta, which is equal to 42 over theta square and minus 4 over theta. And the second order respect to theta, which is equal to negative 84 divided by theta cube and plus 4 divided by theta square. So if this loop equal to 0, therefore this will be equal to 0 as well. So we will have a quadratic equation that is theta times 2 theta minus 21, which is equal to 0. Now, since theta never equal to 0, therefore theta is equals to 21 over 2, or that is 10.5. But the second order at this value 10.5, so if we substitute 10.5 into this, then we will have negative 0.03628, which is less than 0. Therefore, under MLE, the estimate of this parameter theta is 10.5.
Okay, so very obvious for this example. From this data here, that is our individual data. So you need to find, because we have for this question here, we have a deductible and also maximum cover loss. Okay, so that means you have to involve the PDF and also the survival function. Okay, so now you can see that you have to find this data 137,911 actually is the data which is the after deductible apply, okay, after the deductible imposed. So this data actually is for Y. So you need to convert back to the X, because our factor will use the X value instead of Y. You want to use Y can, okay, you substitute the Y, you have to plus the deductible. In fact, actually is the X. Okay, so then in this case, we better try to convert to X first before you substitute into PDF and also the survival. Okay, so you can see all the factor here. That is because this question is saying that the maximum cover loss actually is 14, right? Because the question, if you read carefully, the 11 actually is no, they mentioned the maximum cover loss is 14. Okay, I hope you still remember in my notes I say that for maximum cover loss, that is referred to the X. Okay, we refer to the X. So if your maximum cover loss minus the D, that is become the Y, then this actually is your policy limits, right? The 11 actually is your policy limits. I hope you understand, right? So the maximum cover loss, okay, you minus the deductible, okay? So the deductible actually is how many? Is 3, right? Is 3. So by taking the formula, I hope you still remember. In fact, deductible plus the policy limits is maximum cover loss. That means this 11 plus the deductible 3 is become maximum cover loss. In fact, this 11 actually is a policy limit. So this policy limit always follows the Y. Okay, I already mentioned in the last week lecture. Maximum cover loss is always follow the X. Okay, so when you want to apply the X value inside to the PDF or survival, then we will use the maximum cover loss instead of policy limits. Okay, so please take note. Now, that means we have altogether we have 4 individual data that is been involved the deductible. So we have to use this PDF divided by the survival and deductible. We have 2. Okay, this is incomplete data. After the deductible imposed, that's become the 14 maximum cover loss. So we have 2 incomplete data repeated. Therefore, we will use this factor X, survival at U star divided by survival at D, repeated twice. Okay, so the trick is just like that. It's very simple, class. So next, you try to substitute everything inside to the formula and simplify it. Okay, so if you simplify, you can see you will have this. Okay, you take log likelihood, and then take first distribution, first order and second order. You will get a very simple result. Okay, at the slope equal to 0 and test for the second order, then you can find actually 10.5 is a maximum estimate of this parameter. Okay, so we have covered this MLE. So before I go to next new section is transformation. Maybe I do a simple revision only for this incomplete data. Although, okay, so let me share you. It's very easy to memorize. Not memorize, I mean apply the formula. Okay, so let me show you. So I think you can see this. This is the notes you have. Okay. Not this, I think. You hold on. You hold on. Please hold on. Okay, I share you this. Okay, this is your notes you have. So let's go to the incomplete data. Okay, so for incomplete data, you can see that there are 3. One you may involve the policy limits. Okay, so if you involve the policy limits, then you will have this factor, right? This factor, the survival at U. Okay, now this one actually, if you compare to just now the maximum cover loss, you need to divide the what they call this survival at deductible. In fact, it's the same class. Okay, you see, when it's a policy limits, we just multiply the factor of survival at U. Okay, without divide the survival at D, right? Okay, actually it's the same one. Let me go to next is the deductible D. If you have a deductible D, then you will involve this factor that is your just now the PDF, okay, and divided by the survival. Okay, so this one you know. I want to compare this policy limit and maximum cover loss. So maximum cover loss, you know, I told you this formula, right? Okay, this formula, and in fact, this maximum cover loss is equals to U plus D. Okay, this maximum cover loss actually is equal to U plus D. Okay, so what I want to say is this. Okay, so the maximum cover loss actually is a U plus D, that loss limit plus the deductible. So if your deductible is 0, okay, then this U star will be equals to so if your deductible is 0, so the U star actually is equal to U, right? Is U. So if you look at this, if you look at here, so if you don't have deductible, then your U star is U, right? Then actually this is survival at U, okay? This one will be equal to okay, this will be equal to U star. U star is equal to U. So it's equal. That means if let's say no deductible, so your U star equal to U, right? So it's a survival U at D. But what's your D? Your D actually is 0. Okay, so in this case, this is the same as if your D is 0, so they mean this survival at 0 is 1. Am I right? This survival actually is 1. Then if you substitute into here, it's still the same. So because this survival at 0 is 1. Okay, so you will have survival at U. This is come back to just now the here. It's the same actually. Okay, if you know how to handle a concept, in fact, you no need to memorize so many things because they are the same thing actually. Okay, and U actually remember is right censored, so it's incomplete after the U. That is, we don't have any data. So in fact, this is group data, right? So when you have involved the U, then actually this is a group data that is from U to infinity, right? So you have to understand, right? So if let's say involve just a U, in fact this is group data. Group data we have learned already, right? That is, you have to take the SU minus S infinity, right? Because S infinity is 0. Okay, so actually all these are repeated. You no need to memorize so many formula. In fact, they are the same thing. Group data we have learned already. Okay, because when we apply the U means actually this is incomplete. Incomplete because after the U we don't have any actual information. So if you really want to put into the group, then actually it's a U to infinity. This become a group data already. That is we have learned already in the complete data for group. Okay, so in fact all these are same thing. Okay, so that's how we learn mathematics. We don't memorize so many things. In fact, they are the same concept. Okay, so okay, class. Any question? I have finished this MLE. Okay, for complete data and incomplete data. Okay, so the most important is you need to know the factor. Once you know the factor, you can form the MLE, and from there you may find this differential equation. Log likelihood. Okay, or no need. Okay, some question very unlikely class. Very unlikely that some you no need to take if likelihood. You can direct differentiate. If the likelihood so simple, why you want to take a log? Okay, for example, let's say maybe your likelihood equation, for example, class. Okay, for example, maybe your likelihood. I just simply type. Okay, let's say. Hold on, let me finish first. I just assume, okay? If let's say your likelihood is like that, just a theta cube plus 4 theta, are you going to take log? What for? If you take log, I think more complex, right? I can direct differentiate. If I differentiate this, it becomes 3 theta square plus 4. That's it. Am I right? Okay, of course, I should put the negative here, then meaningful. Okay, so if let's say my likelihood function is like that, why you want to take a log? If you take a log, much more complex, right? So I prefer I differentiate straightforward. Take dl d theta, this becomes 3 theta square minus 4. Okay, when the first order equal to 0, I solve the problem. Okay, assume class. I just assume this. Okay, maybe this is a negative by right, this is negative and should be like that lah. Then only you can get the maximum. Okay. So what I mean is that it's not necessary to take log likelihood. Okay, but most of the problem you need to involve because most of the function involve the exponential, the PDF or whatever involve exponential. Some much more complex. Therefore, you have to take the log. Okay, so I have done for this. We go to transformation now. Okay. Now, transformation actually is quite easy. Okay. Why you want to learn transformation? Because transformation is another method to measure or to calculate the parameters. Okay. So the method I can show you. Okay, you hold on. Because just now I delete off all my videos, so I have to call back. So let's go to part 13. Okay, so transformation class. We try to transform from one of the distribution to another distribution. Okay, so based on MLE, we have one property that is based on the exponential. Okay, we based on the exponential distribution. You want to transform certain, let's say certain distribution, you transform it by certain condition. Eventually, you will transform the other distribution become exponential. So once you can transform to exponential, then you can use a property of the exponential to determine the parameters. Okay, I show the example or from another, you learn better. Okay, let's carry on.
Section 4.3, Transformation. MLEs are invariant under one-to-one transformations. If you have a transform variable, you can untransform it and calculate the MLE of the untransformed variable. Depending on how the parameters were modified when performing the transformation, we may have to modify the results. Several distributions are fairly direct transformation of the easier known distribution. As a result of this transformation, we get a simplified method for estimating parameters in this distribution using maximum likelihood relationships from an exponential distribution. So by using transformation, let Y is an unknown distribution with a parameter, and this can be transformed where the Y become exponential distributed with another parameter. So under MLE, we can find this parameter for this exponential distribution. Then this parameter will be equal to the summation of xi divided by the n, which is equal to the sample mean. And so, from this parameter, we can determine this parameter of y.
So do you understand this algorithm here? Let's say my y, that I want to find the parameters of this distribution y. Okay, so this parameter usually you may have more than one, you may have 2 or 3. Okay, so the exponential actually only got one parameter, remember? Okay, so we only, here maybe you have 3 parameters, but we only can determine one parameter. In other words, the other 2 parameters will be given. The value of the parameter will be given, is known. Only one parameter is unknown. That unknown parameter from y I can determine after transformation. I can determine by this exponential. That is this y distribution. After transformation, this distribution can be anything. It can be gamma, can be Pareto or whatever. But eventually, this y can be transformed to exponential. Okay, so from this exponential, I can use this sample mean formula to calculate the parameter of this exponential. And in other words, this parameter also can determine the parameter, unknown parameter from the y. Okay, so maybe you have a little bit concept now. Okay, let me go to further. This inverse, we go to next is the inverse exponential. You see how I transform. Okay, how I calculate the parameter for this inverse exponential distribution.
So before we go further, let's prove it. Suppose a random variable x has a sample of n observation, that is from x1 to xn. Let x follow an exponential distribution with the parameter theta, that is x is exponential distributed with this parameter theta, where the PDF is given by this. Then we will have the following likelihood function, that is the product of all the PDF corresponding to the x values. And if we simplify this, we will get the following result, and this is equivalent to this in terms of summation of xi. And next, we have to find the log likelihood function, that is, this will give me negative 1 over theta times the summation of xi and minus n log theta. And therefore, the first order will be equal to summation of xi divided by theta square and minus n divided by theta. And the second order, which is equals to negative 2 summation of xi divided by theta cube, and this will give me plus n divided by theta square. If this look equal to 0, therefore this will be 0 as well. Then we will have a quadratic equation, that is theta multiply theta n minus the summation of xi, which is 0. Now since theta never equal to 0, therefore theta will be equal to summation of xi divided by n. But the second order with this value, that is when we substitute this value into here, then we will have negative n cubed divided by summation of xi square. And since n is positive and this is always positive, then the whole thing is negative. And hence, under MLE, the estimate of this theta, which is equals to summation of xi, where I stick from 1 to n divided by total sample size n. And this is actually equals to, is a sample mean.
Okay, so for this section, I want to prove to you that under MLE, for this exponential distribution, later I'm going to show many distribution transformation on many distribution. Okay, but before we transform, we have to know this concept first. That is, I try to prove to you first. I'm going to prove that the x distribution, the exponential distribution, after MLE, okay. So like what you've done under this individual data, you form the likelihood and try to get the log likelihood. After that, you do everything. You can see that at last, this parameter data from the exponential distribution just now actually is equal to this. That is summation x divided by n. So I want to show to you under MLE, this data from the exponential actually is just a sample mean, right? It's a sample mean, like what we have learned in the method of movement, right? It's exactly the same. So I'm going to use these properties later, okay? Under MLE, I'm going to use these properties for distribution to prove, to show or to find the other parameters from other distribution. Okay, let's carry on. I go to next inverse exponential now. How I going to find the parameter? Okay. Okay, so now we go to inverse exponential.
Inverse exponential distribution. If x has an inverse exponential distribution with the parameter theta, then 1 over x has an exponential distribution with the mean, which is the parameter 1 over theta. Therefore, the MLE of theta for an inverse exponential is obtained by calculating the MLE of an exponential on the reciprocal of the theta. And then inverting this MLE, then we will have this result. Let's prove it. Suppose a random variable x is inverse exponential distributed with the parameter theta. Let y be a random variable such that y is equals to 1 over x.
Okay, this is important, class. The algorithm for the transformation is easy, right? It's very easy, but only this is the keywords that you have to different distribution of the transformation that you will have a different formula. Okay, so in exam, my paper usually I will give this formula. You no need to memorize. Okay, for my test paper I will give. Okay, of course, in professional paper they will ask you to prove lah. Okay, so when you want to prove this this equation will be given. Okay, you no need to memorize. So I will use this formula, then I will transform. You see how I do it.
Then, by transformation, we have the following. So the CDF at y, based on this random variable y, which is equals to the probability where the y is less than the y value. And now we substitute this y as 1 over x, which is less or equals to y. And when we arrange, we will have x is greater or equals to 1 over y. And this will be equal to 1 minus the CDF at 1 over y based on x. Since x is an inverse exponential, then we can get the CDF formula from table C, and so we have this result. Minus theta from this parameter divided by the x value, that is 1 over y. And if we simplify, we will have 1 minus e to the power of y divided by theta to the power of -1.
Okay, class, before move to next step, for this inequality, when you rearrange, because the sign may change, understand? This inequality sign may change based on the value of x. Here, because I couldn't write, okay? Now you look at here. I hope you can see my mouse is moving. This is a 1 over x, right? It's a 1 over x. So you bring the right hand side, then the x will be greater than 1 over y. That is you have here. In fact, the notation of this inequality didn't change, because this is 1 over x. You bring over the right hand side, okay? The inequality didn't change, okay? This only for the survival of this theory, class. The sign no change, but in other subject it may change, okay? Maybe I finish this example first, then I show you something, okay? This is about mathematics, okay? For the inequality. Let me finish this example first.
So in other words, we say that this y, which is equals to this random variable x to the power of -1, is exponential distributed with the parameter of theta to the power of -1. So based on this exponential distribution, therefore, this parameter, which is equals to the sample mean, that is the summation of this observation from I is 1 to n divided by the sample size, that is n. And we rearrange this, we will have 1 over theta, which is equal to the summation of 1 over xi, where I is from 1 to n divided by n. So therefore, theta is equals to n divided by summation of 1 over xi, where I stick from 1 to n. And this is our estimate of parameter under MLE.
Okay, class, are you clear from here? Since you have transformed, when you want to transform, you must go to CDF. Just like we want to, in this theory, we involve the, what they call this, scale distribution. Okay, you have to start from the CDF respect to y, based on y here. So you start from this step, like you prove the scale distribution. Okay, so you can see eventually this is what they call this inverse. This is exponential, right? Maybe I share the Word document. You hold on, Okay, so this is a 1. So you can see from this what they call the CDF, right? This CDF I convert to here, that this one actually is last year you can see it's exponential. You know that your y actually is inverse. Okay, your y actually is inverse of x. Okay, so when I try to transform, eventually this become exponential. That means this y actually is exponentially distributed with this parameter 1 over theta. Okay, it's 1 over theta. So when this is an exponential distribution, then of course you can use the formula, the properties of exponential, that the summation of how to say here. You can see how I take this the observation. Okay, I take 1 over xi. Okay, 1 over xi. Unfortunately, I cannot find. I should plug my. Hold on, let me see whether it works or not. No, it's okay. Now look at here, class. I take the summation of 1 over observation. Why is 1 over x? Because my observation actually is x inverse. That's 1 over x. Okay, so whatever this x here, the pattern, you just copy only. If this is a x to power 3, then this will be x power 3. Okay, if this is a sine x, here will be summation of sine x. You just follow the pattern from the random variable x. Okay, definitely this must divide by n, because the exponential distribution, the formula is this, right? Remember, if I write here. So remember, if let's say, if my x is exponential distributed with parameter, let's say I put lambda. Okay, if my x is exponential with the parameter is lambda, so what is my lambda? Okay, so the parameter of this lambda will be equal to this. You hold on. Okay, so this one we have learned, right? Just how I have proven to you. If x is exponential distributed with the parameter lambda, then lambda will be this. Okay, if let's say I put my x power 3, okay, my x if this power 3 exponential distributed with this parameter lambda, so what's my lambda? Then my lambda will be equal to this summation. Okay, because you can see the x cube here also follow. Okay, let's say what happened if let's say like that. Let's say now my x cube is exponential distributed with the log lambda. Okay, so then this become log lambda will be equal to this. You just follow the pattern. I hope you understand. Because the log lambda actually is just a data. Okay, the x cube, in fact, it's just y. Okay, so this become you follow the pattern. Please follow the pattern. So here, I hope you understand that what I try to explain. So from here, if from this step here, if I found that eventually it's exponential distribution, then if we found this result, then easy job. Then we will use this concept. Okay, to get this connection. Then after that, you get the result. I think it's very clear now. Okay. Now, just what I want to say is here. Okay, I want to come back to here. That when you want to do your when you want to simplify your inequality, okay, because for risk theory and survival model, we have a special offer, so-called. That is the inequality won't change. I tell you what. You hold on. Let me. I try to write something first. You hold on. Because when I type in a math type, the Microsoft team, I think, cannot read unless I come out from the math type. So I can see this is equal, right? okay, the inequality would not change yet. Okay, now I move to next step. So if I move to next step, I will have the following. Okay, you will have this. Okay, you can see now my x is going up to the right hand side, the y go down to the left hand side. The inequality not change as well. All right. So in fact, this is equal to this. Okay, so if I move to next step, so you will have okay, so look at here. It's the same, right? But in fact, the last two line here is the same, but the inequality not change actually. Okay, so what I want to say is why is no change? You move x up and down, or you move your x left to right here, the inequality won't change because our x and y is referred to the claim or loss random variable. It's a money. So our money is no negative value. Therefore, the inequality won't change. But in other subject, into the plot or into the stat, it may be changed because your value maybe have negative. Understand? So you have to be careful. You have, when you want to prove the formula, you must know what is your x and y random variable. So for our case here, we assume that all our x and y never take negative. So therefore, you can simply bring up and down, left to right. Okay, we no need to bother about the sign, whether change or not. Okay, so this is the advantage in risk theory and survival model. Okay, so I hope you get it. Okay, so now we come back to just now the slide, and we want to go to the example. Okay, so we have proven. Okay, we have proven just now this the data. I want to find what is my data for this inverse exponential. I want to show that what is my data parameter data for this inverse exponential. Okay, so I use transformation. I start with this equation, y equals to 1 over x. Okay, so you don't worry about this. I say already, unless you're very strong in risk theory or survival model, roughly you will know what equation you want to take. Okay, otherwise you just memorize, or otherwise you just refer to the books or notes. Okay, then you do transformation. Okay, when you do transformation, then you can get the connection. Okay, so you can see I transform. Eventually, it's become exponential. Then I use in exponential to get the parameter, okay, of the inverse data. Inverse data actually, this 1 over data is a parameter of exponential class. Okay, you have to know that I'm doing exponential. I'm not doing inverse exponential. This 1 over theta is a parameter of exponential. So when I have a 1 over theta, I change it to theta. Now theta is the parameter of the exponential, inverse exponential. Okay, 1 over theta is the parameter of exponential. If I convert to theta, and this theta now is the parameter of inverse exponential. That's a trick. Okay, so we have done proving this formula, how to find. Now later I won't explain so detailed class, only this one because the step. You will know this step for inverse exponential, the rest almost the same one. Okay, now we move to example 11. I want to save the time because this is very easy one. All these examples very easy. Maybe we just go to the question first.
In the study of insurance claims, you are given the following sample of 4 losses. You are fit to an inverse exponential distribution with mean data to this data using maximum likelihood methods. Calculate the resulting estimate of the probability that a loss is less than 5,000. Let x be the claimed random variable such that x is inverse exponential distributed with the parameter data. So our aim for this problem is to find the probability when the loss, which is less than 5,000. So in other words, we have to find what is this value of the parameter data. Then we can use this result to solve the problem. Solution for
Okay, so here I skip to it because very easy, right? Okay, so I need to find the parameter of this data. So to save the time, so we use this formula. Okay, substitute all your observation inside this formula. You can estimate the parameter data for the inverse exponential. Just substitute, okay, all the value. You will have the data actually is just 2442.75. Once you have this parameter for this inverse exponential, then we can solve this problem by using the formula from table C. Okay, you will get it. It's just about 0.6135. Okay, so just apply the formula only. Very simple. Okay, so now I move to maybe I move to next question. Next section. 14, 15. You hold on. Okay. So now we go to Weibull distribution. We have learned transformation of inverse exponential. Now we go to Weibull. Okay, I also can estimate the parameter for Weibull distribution by using transformation.
Weibull distribution. The Weibull distribution is a transform exponential distribution. Suppose a random variable x has a Weibull distribution with parameters theta and a known tau. Then the random variable x to the power of tau is exponential distributed with the mean, that is theta to the power of tau. So here, for a Weibull distribution with parameters, so under MLE, if tau is fixed, then the MLE of theta is given by the following formula. Proof. Suppose a random variable x is Weibull distributed with the parameters theta and tau, with the tau is known. Let y be a random variable such that y is equals to the random variable x to the power of tau. Then by transformation we have the following. That is the CDF at this y value based on random variable y, which is equals to the probability when y is less or equals to this y value. And we try to substitute the y as x to the power of tau, and which is less or equals to y. And this will give x which is less or equals to y to the power of 1 divided by tau. So this is equals to the CDF at this value based on random variable x. So since x is a Weibull distribution, then this will give 1 minus e to the power of y to the power of 1 over tau divided by theta to the power of tau. And this is equal to 1 minus e to the power of negative y and divided by theta to the power of tau. And obviously, this is an exponential distribution, and in other words, this y, that is x to the power of tau, is exponentially distributed with the parameter theta to the power of tau. Then, this exponential distribution will give this parameter, which is equal to the sample mean, which is equal to summation of xi to the power of tau, where I take from 1 to n divided by the total sample size n. So we arrange this data is equals to the summation of xi to the power of tau. I is from 1 to n divided by n to the power of 1 over tau. So under MLE, this is the estimate of the parameter data of Weibull distribution when tau is fixed.
Okay, so class, for this Weibull, I need to estimate the parameter of data if tau is known. Okay, let's say tau is given. I want to find what is the parameter value for this data by using transformation. So when what is transformation, again, I told you just now, the formula is important, right? This one you no need to worry that y equal to x power tau is given, okay? So by using the CDF respect to y, okay, then you eventually you can see you will get actually exponential distribution, okay? So that means this x to the power tau actually exponential distributed with this parameter theta to power tau. So I show you. Once you get this exponential, then the rest very easy. You can use a sample mean we have proven just now for exponential. Then you can get this this parameter of theta to power tau. Okay, that is this. So remember, this parameter theta to power tau is the parameter of exponential class. It's exponential. Our aim is to find theta. Theta alone is the parameter for the Weibull. So I just throw away the tau to the right-hand side, then I solve the problem, right? So this is the parameter for the Weibull. You will transform to exponential. Any distribution you transform to exponential, we use the sample mean for the exponential, then you can get the parameter of the distribution that we want to find. Okay, so we have done this. So next, I think we go to the example. Example also we just read the question first.
A random sample of 8 values from a distribution x is given as follows. Assuming that x is from a Weibull distribution with the parameter tau is 1.1, find the MLE of data and the MLE estimate of this probability when x is less or equals to 10. Now, since x is Weibull distributed with the parameter theta and the tau, which is 1.1, so our aim is to find the estimate of this parameter theta under MLE and also the probability when x is less or equals to 10. So by using this formula, since the tau is fixed, then we can estimate the parameter theta, and hence this problem solved.
Okay, so this example job also I can skip. I can go fast speed because it's very easy. So from this observation, we substitute into the formula that we have proven just now. Try to find the parameter of this Weibull. Okay, so just substitute only class all the x value. Of course, you must know how to handle the formula. I assume that you know how to handle the summation and substitute the tau value because the tau is 1.1. Okay, so at last you can get 14.34. This is parameter value. Then here you can get the CDF from table C under Weibo. Okay, you will solve the problem. Okay, that the chances is about 50%. Okay, so this is your Weibo. Okay, please take your attendance.